Swayam Prabha. Digital India. Educated India.
Welcome back. So, we will today start with a numerical example on solving a equation, I mean a more complex circuit using impedances, and then after that we will try to move on to how to calculate active power, reactive power, apparent power, and some of the concepts which are related to utilization of the electrical energy. So, to start with, continuing from the theme where I left behind in the last class, let us say that I have a circuit like this, and let us say that there is a resistance of 1 ohm. Let us say that there is a inductance of, or I will write it as J times of 1 ohm. So, which means that it is a this is 50 hertz supply, let us say 230 volts, and in series with this is a series parallel combination of another R and L, which is of, let us say 0.8 and or let me take it as 1 by 0.8. So, 1.25 ohms and 1 by 0.6. I am just trying to choose numbers in a better way. So, this is 5 by 3 and this is 5 by 4. Again inductance of J and ohms. My question now is, one. So, what is the, let us say this is a load. That means load means something to whom, like for example, my home is a load on the distribution system, on the supply that is coming to me, or if I put something in a plug socket, let us say a microwave, and switch it on, then on my residential system that microwave becomes a load. So, in that sense this is the this is the load, a resistive RL load, and let me reduce these numbers a bit further. Usually supplies will not have, so let us say this is 0.1 and 0.2. So, these are for example representing a supply wire for example, or even better would be probably a number like 0.2 and 0.1 ohms, of course inductive. So, J has to come, this is the inductive reactance of it. So, a very typical kind of example this is. Usually wires are having inductance associated with them and resistance associated with them. So, this is representative of a wire, this is representative of a home supply, and this is representative of a load which is connected to it. And our question is now, what is V L, this voltage across the load. So, move it to a bit of a center stage, and question is what is this, what is the V L, that is question number 1, and question number 2 in any order you can take, what is the current supplied by the source. So, question is what is the current supplied by the source, that is the A part of the question, and B part of the question is what is the voltage V L at the load. In fact, we can ask one more question, what is the voltage regulation. Okay. So, first of all, let me just define what I mean by voltage regulation. So, my supply is V s, my load voltage is V L, these are the magnitudes of the phasors that I am showing, into divided by magnitude of V L into 100. This percentage is known as the voltage regulation. Suppose these wires were perfect wires, that means this impedance here was 0, then V L would always be equal to, V L will always be equal to V s, and so 0% voltage regulation is an ideal which is not achievable, but we want voltage regulation to be low as possible, maybe generally speaking we want the voltage regulation to be low. Now, let us start working on this circuit. To be more consistent with the real world, I am going to take this as the peak amplitude of our supply is not 230 volts, but 230 into root 3 volts. So, I am going to take this as 230 root 3 volts, because right now my phasor I am associating it with the amplitude or the peak value and the angle which is associated with it. Now, at this point of time there is no reference given to you. If you observe carefully in this problem, at this point of time I have not given you any reference. So, you are free to choose anything as a reference. I am going to choose the supply voltage V s 230 volts root 2 at an angle 0 as my reference. That means, what I am saying is that this is the V s is what I am assuming. See, all the current that will be calculated, it is relative to this phasor. Suppose this V s I rotated to vertical line, and suppose the angle that the current makes with respect to V s is 30 degrees, then if Vs is rotated to 90 degrees, if the Vs is rotated like this and initially the current is like this, then if the Vs is taken this as the reference, the current will come out to be this. So, the angles are only relative, and in such a simple circuit, really there are not many choices also available to us. Either we could have chosen VL which we want to compute, the VL which we want to compute as the reference, or we can choose this as the reference, and choosing reference usually means associating an angle 0 with it. And in this particular case, I do not need to even say whether I am choosing a reference as sine wave or a cosine wave. It is irrelevant, because I am only asking you for the phasor values of the voltages and current. So, those are anyway algebraic numbers. Whether the sine is the reference or cosine is the reference is a question that you will have to answer. If I ask you, if you are asked something in time domain, a waveform structure in time domain, which in practice nobody is going to ask you. Though our supplies are sinusoid, you do not see sinusoid anywhere, right. You just see bulb glowing, you just see geyser heating, you just see microwave rotating, you just see TV functioning. So, even though and mostly, but we are more concerned with voltages, whether it is low or high, current whether it is low or high, power with what is the power, and so on and so forth. But directly sinusoids are sort of somewhere hidden behind the common man, he does not see that very clearly. Okay. Now, to solve this circuit, what we see is that it is a combination of two series, two blocks coming in series. This itself is a series and this is a parallel block. So, what we need to do is first of all calculate the net impedance of this parallel block, and then add that to this impedance, the wire impedance, and then we will get the total impedance of this whole subsystem, and that comes across this voltage source. So, then we can apply the Ohm's law and get the current. So, now because this is a parallel circuit, so what we are going to say is its 1 by Z is going to be equal to, we have to, it is a just like parallel resistors, we have to just add the parallel combination reciprocal of the impedances. Actually, one is just a resistance, one is just a inductive reactance, and we have to add the reciprocal of this, and this leads us to the reciprocal of the net impedance. So, this is going to be 4 by 5 minus j times 3 by 5. So, 4 minus j 3 by 5, which is 0.8 minus j times of 0.6. So, this is my 1 by Z, and the Z is going to be equal to reciprocal of 1 by Z. So, this is not ohms, 1 by Z will be mhos, so many mhos, and the reciprocal of this is 4 minus Z is this much ohms, and if you multiply the denominator by its numerator and denominator by its complex conjugate, then you get this, which is 5 by 25 into 4 plus j 3, which is 4 by 5 is 0.8 plus j times of 0.6 of ohms. So, now you can see that I have chosen nice numbers, so that 1 by Z and Z calculation turns out to be simpler. This is just for the sake of illustration. Numbers can actually be more rough than what I have chosen here. So, this becomes the Z of our, let us call this as Z2. So, whatever is here, let us call it as Z2, whatever is here, let us call it as Z1. So, Z 1 is 0.2 plus j 0.1 and ohms again, and so Z net which is equal to Z 1 plus Z 2 is going to be equal to 1 plus j 0.7 ohms, and therefore, 1 plus j 0.7 ohms. So, therefore, the current which is phasor which is being drawn from the supply, the current phasor which is drawn from the supply is V by Z net. So, this voltage of 230 volts root 3 root 2 at an angle 0 is coming across this Z net branch, and so by Ohm's law this is going to be equal to 230 root 2 divided by 1 plus j 0.7, or in other words 230 root 2 divided by, again multiplying and by the complex conjugate of the denominator on the numerator and denominator. This is 1 square plus 0.49, which is same as 230 root 2 divided by 1.49 into 1 minus 0.j7 into 1 minus 0.j7 amperes. So, basically this is 230 root 2 by 1.49 into 1. This component is 230 root 2 divided by 1.49 into 0.7, and this component is, this becomes my I. So, you can approximate this. I will just do an approximation of this. I will take the denominator to be 1.5, 1.5 will be 3 by 2 into 1 minus j 0.7. So, 460 by 3 into 1 minus j 0.7. So, this is going to be 1, 5, 3 root 2 approximately, again I am just writing this, into 153, it will be point something, but I am not worrying right now about that, into 1 minus j 0.7. So, this is actually a large current. Actually, these impedances will be at least 10 to 100 times this particular value. They will not be so small. I knew it when I took it itself, that they will be much larger than this, and this much 153 amperes, none of your fuse is going to, I mean your fuse, if you look at it, you have 5 ampere, 10 ampere, 15 ampere, that is the kind of rating of the currents that you see in your home appliances. 153 which I have got in this numerical example, which I just cooked it on the fly, is way out of bounds. Anyway, now the next question was, what is the voltage VL across the load? So, that is going to be 230 root 2 angle 0 minus this current times Z1, is it not? If I take this drop, this is one way of calculating it, or other way of calculating it is same as I times of Z2, and I we know, Z2 also we know. So, I will choose the other one, I will choose the other one. So, Z2 is 0.8 plus j 0.6 and IL is 153 into 1 minus j 0.7, and whatever comes out here is going to be your this is going to be your so many volts, and this number is going to be, I will leave it to you to calculate this number and see what this number is. So much of volts will be coming out, and then once you know this, the percentage, so there are some blanks which you have to fill up. The percentage regulation is 230 root 2 minus whatever is the magnitude of this VL. Now, you can see that because these are complex numbers, we are writing them by their magnitude into 100. This is going to be your voltage regulation of this particular circuit. So, that is the important take, that once you are able to write the complex numbers, see inductor is given by this, right. So, its phasor representation, roughly speaking, I am not, in fact, it is not roughly speaking, it is strictly what we can simply do, this d by dt operator, which is also called as a p operator, we can replace it by j omega. What is the reason for that? The reason for this is the derivative of this is nothing but this, and last class we saw that complex exponential, we can work directly with complex exponential, and once we can work with the complex exponentials, then this d by dt operators can what this shows about to this, what this shows here to you is that d by d, anywhere a d by dt operator comes, you can replace it by j omega, where omega is 2 pi f, for India it is 2 pi into 50, that is about 100 pi. So, radians per second. So, therefore, VL phasor is the moment you talk with complex exponentials or sinusoids, you are dealing with phasors. So, VL j omega L IL, in other words, what we are saying is this is the unit being ratio of voltage to current being ohms. This is the inductive reactance. Similarly, for a capacitor, our equation is IC is equal to C dVc by dt. Again, when dealing with complex exponentials or other words sinusoids, what we will do is we will this p operator d by dt, it is called a Heaviside operator also, we will replace it by j omega, and we get the equation in phasor form as j omega c times of V c. So, therefore, the impedance is 1 by V c by I c is 1 by j omega c or minus j by omega c ohms, and the admittance, which is the reciprocal of the impedance, is simply, or the B, because there is no real part here, is simply j omega of c. So, this can also be written as j b into V c amps. So, this the moment you have j coming into picture, you know you are dealing with sinusoids, you know you are dealing with complex exponentials, and if somebody gives you directly the values in ohms, then it means appropriate multiplications by 2 pi omega equal to 2 pi 50 or 2 pi 60, whatever it is, those substitutions have already been done. So, this is capacitive reactance. And with resistors, of course, you know that this is nothing but equal to resistance, that is the voltage and current across a resistor are in phase with each other. Okay. Now, I need to give you some more idea of I want to bring you back to the Euler's identity. I want to bring you back to the Euler's identity and interpret J as an operator which does 90 degrees rotation and hence indicates a unit vector along y axis. So, this is one next task that I want to do, because until I have done this task I have really not connected vectors at the complex numbers, and before I launch into power related calculations I did like to put to rest this connection between the vectors and the j operator and the complex number. So, get back to Euler's identity. Let us get back to the Euler's identity. What was e to the power j theta? E to the power j theta is cos theta plus j times of sin theta. This we have already seen. So, now let us put theta equal to 0 degrees. So, what does this come out to be? This comes out to be 1 plus j 0. Let us put angle of 90 degrees. Then what does this say? Cos of 90 degrees, which is 0 plus j times of 1, and then if you put it as minus pi by 2, sorry, if you put it as pi, if you put it as e to the power j pi, then it becomes cos of pi, which is minus of 1 plus j sin of pi, which is 0. So, it is minus 1, and if you take it as e to the power j 3 pi by 2, then this is going to be equal to 0 plus, in the similar lines it is going to be equal to 0 minus j times of 1. So, now let us try to sketch each of these complex numbers here. The first one is a unit length vector like this, 1 plus j 0. The second one, because it is associated with 90 degrees, is a unit length vector like this. The third one is a unit length vector like this, the minus 1, so the direction has changed, and the fourth one is a unit length vector along the y axis, because the angle is 3 pi by 2. So, from the angle I am taking x axis as the reference, and I am calculating angle I am plotting from here, and then I am trying to map this. So, I get first, second, third and fourth. So, if you complete this, this is a circle, this is a unit circle. What I have got here is actually a unit circle, what I have got here is actually a unit circle what I have got is a unit circle rotating in 0, pi by 2, pi and 3 pi by 2, each of the length 1. Now, if you look at e to the power j theta, it is cos theta plus j sin theta, and this is my interpretation that the j operator is nothing but the 90 degrees rotation operator. So, the j operator basically means rotate everything by 90 degrees. So, why? Because if you say e to the power j theta, then it is e to the power j theta into e to the power j pi by 2, which is e to the power j theta plus pi by 2, which means that this e to the j theta operator is rotated by 90 degrees. So, therefore, default it indicates the y axis, the x axis being at one angle 0, unit vector along the x axis being one angle 0, rotated by 90 degrees, where what in anti-clockwise direction, what do you get? You get the unit vector on the y axis. So, therefore, the j operator basically indicates the unit vector along the y axis. Now, if you take this as e to the power j theta, then what it means? Its projection on the real axis is cos of theta. So, let us say I take a vector at an angle theta from the x axis, then what it says is it's project it now on the x axis, I am sorry. So, project it onto the x axis. So, this projection is cos of theta. The projection along the y axis, which is indicated by j sin theta, because sin theta is just a scalar and j has an angle of 90 degrees. So, this is the projection on the y axis sin of theta. This is along the x axis, because the angle associated with it is one angle 0. So, therefore, this is cos of theta projection sin of theta, and cos square theta plus sin square theta is 1. And this is correct also with respect to the this being theta, this angle being theta and this being a unit length vector, its projection on the x axis is cos of theta, its projection on the y axis is sin of theta. So, now it is clear to you that e to the power j theta actually indicates a vector which is at an angle unit vector. Why does it, why do I call it as a unit vector? Because modulus of e to the power j theta is 1. So, it indicates a unit vector at an angle theta with respect to the x axis. Now, suppose theta was omega t, this is something that is going to happen quite often, that actually theta will be omega t, then this means this is cos of omega t plus j sin of omega t, and if theta is equal to omega t, then we know that d theta by dt is going to be equal to omega. So, it means that this particular vector, this unit exponential vector here is rotating at a speed of omega. So, it is rotating at a speed of omega radians per second. So, that is what e to the power j omega t symbolizes. So, we have connected now a vector. Suppose this is a vector, okay. It makes an angle of theta and its projection along this is a vector is ax and its projection on the y axis is ay. So, that I can write this vector as ax plus this vector ax plus the means usually we will write it as I plus using your coordinate geometry notations you will write it like this. So, now in our case this a vector has become ax plus j, where j is under root of minus 1 times of ay, and so this is just a complex number. So, a vector is effectively a complex number. Its real part is actually the its projection on the x axis, its imaginary part is its projection on the y axis, and the value of the vector is ax square plus ay square under root. So, this is the magnitude of the vector. So, now vectors, instead of adding vectors, suppose I give you one vector, let us say 1 at an angle of 30 degrees, another vector let us say I give you point root 2 at an angle of 45 degrees, and I ask you to add these two vectors. So, one thing is that you would say that parallelogram law of identity can be applied and the angle between the two vectors is 15 degrees, and so the length of the vector is 1 square plus under root of 2 square plus 2 into 2 AB. So, 1 into root 2 into cos of 15 degrees, and then you will calculate this angle by doing the appropriate projections, and this seems to be pretty cumbersome thing to do. Instead of that, what we will do is we will write the vector v1 what we will do is first vector v1 we will write it as 1 cos 30 degrees plus j sin 30 degrees, or in other words 1 into, or in other words root 3 by 2 plus j times of half. The other vector v2, so this is v1, this is v2. The other vector v2 we will write it as root 2 cos of 45 degrees, which is 1 by root 2 plus j sin of 45 degrees, which is also 1 by root 2, which amounts to taking it as 1 plus j1. So, now if I ask you to do the vector addition, then this is 1, you add the real parts together and you add the imaginary parts together, and so this is going to be 1.866 plus j times 1.5. So, you this is let us say the new vector v. So, the magnitude of this vector v is nothing but square root of 1.866 square plus 1.5 square, and the angle that it has, this is the polar notation, is tan inverse of 1.151866, and geometrically this is make this as 1.866, make this as 1.5, connect this, and this is your vector v, and this is the angle theta, which is tan inverse of 1.5 by 1.866. It is in the first quadrant. So, you can see comparative to parallelogram law of identity, doing it through complex numbers is so more easy, and you can also see because of what I did here, that the d by dt operator can be replaced by j omega. Because of this, you can also see that it is able to handle differential equations also. Complex numbers allow us to play with the first order differential equations also with ease. So, both vectors and differential equations, these are the two things which we have to bother when we are solving our circuits. Both of them are neatly handled through complex numbers, and therefore, you would find that all phasor analysis in electrical engineering is done using complex numbers. Now, let us let me discuss a bit about real power, reactive power, the concepts let me introduce to you of, and the concept of apparent power. So, suppose that I have a source V t which is given by V m sin of omega t, and let us say that this source supplies a load Z L which takes a current of sin of omega t minus phi. So, phasors if I want to show, naturally I will take V m as the sin omega t as my reference phasor. This, so the V t waveform is this is the I t waveform, and it lags the inductor, it lags the voltage supply by the current, lags the voltage by the angle of 5 degrees. It is a inductive circuit. Now, every instant to instant, if you multiply v into v times of I, what you will get is the instantaneous, power v into this, which is Vm Im into sin of omega t minus of phi, which can be written as Vm Im by 2 into 2 sin A sin B, which is cos of A minus B, which is cos of phi minus cos of A plus B, this is A and this is B, 2 omega t minus of phi. So, what I have done is I have written sin A sin B as half of cos of A minus B minus of cos of A plus B. So, to make it a bit more symmetric, I am going to write this as V by root 2 into Im by root 2 into cos of phi minus cos of 2 omega t minus phi, and incidentally this is the root mean square value of Vm. I will come to this, and Im by root 2 is the root mean square value of the current. I will again come back to this, and so instantaneous power P of t is going to be equal to cos of phi minus of cos of 2 of omega t minus phi. Now, something interesting comes out of this. If you want to sketch this, it has a average value of this Vrms, Irms cos of phi, and then a double frequency oscillation, a double frequency oscillatory component, which is of 2 omega of t, which is double frequency because of this term 2 omega, which is coming with respect to it. So, two questions come to your mind. The first question is, what is the average value of P of t? What is the average value of P of t over one cycle? One cycle means one time period. So, P of t average value over one time period t is going to be integrate this, I have to integrate from 0 to t into P of t of dt. Now, the first component Vrms Irms cos times of phi is a constant. So, therefore, when you that will be taken out, and when you integrate it from 0 to t times dt, you will get a t which has to be multiplied by 1 by t. So, therefore, you get unity. So, therefore, the first component is going to be just Vrms Irms cos of phi. So, the first component is going to be Vrms Irms cos of phi, and the second component is just a double frequency oscillation over one time period, and therefore, it is going to be 0. So, if you look at what I mean to say is, does not matter what this phi is, if you integrate it from 0 to t 1 by t, this is going to be equal to 0, and that is quite straightforward. This is sin of 2 omega t minus phi by 2 omega 0 to t 1 by t, but this is sin of minus phi minus sin of minus phi by 2 omega t, which is 0. So, algebraically also you can see that it is 0, or to sketch it, let me take phi equal to 0 for the sake of discussion. So, I am looking at cos of 2 omega of t. So, if you look at this waveform here, let us say this is the cosine waveform, this is 2 pi, this is 0. So, now my goodness, now I want to write this is the fundamental frequency waveform. Now, I want to introduce a double frequency waveform here. So, the cos of 2 omega t would actually turn out to be reaching the maximum negative peak here. It completes one cycle, it completes another cycle here, not come out very well. But you can very clearly see that whether it is the fundamental frequency waveform, the area that it covers in one cycle is 0, because is 0, because this area and this area 1/4 of a quarter add together and make 1/2 cycle area, and this is the negative 1/2 cycle. This is the negative 1/2 cycle area. This is quarter cycle area, together one cycle half cycle area. This is a half cycle area, equal and opposite signs. So, therefore, net sums out to be 0. And if you look at the same thing now with respect to the double frequency waveform. So, I will remove this. Now, if you look at with respect to the double frequency waveform, again this area will cancel out with this area, equal and opposite quarter cycles. Again equal and opposite quarter cycle cancels out with this area. So, 0. This area cancels out with this area cancels out with this, and so symmetrically every quarter cycle is compensating with the next quarter cycle. So, therefore, the angle which is going to be, so the net area enclosed is again equal to 0. So, in general is 0 in general. And now, I will just show you, because I like to connect it with complex exponentials also. So, I do this if I look at this is 1 by omega t 0 to 2 pi e to the power j omega t minus of into e to the power minus of j phi into d of omega of t, which is same as you take e to the power minus j phi common, integration from 0 to this e to the power j theta times of the theta 1 by 2 pi, which is e to the power minus j of phi into e to the power j 2 pi minus e to the power j 0 by 2 pi, which is e to the power minus j phi 1 minus 1 by 2 pi, which is 0. But then if you look at this left hand side, this is nothing but integration of, by Euler's identity, cos of omega t minus phi plus j times of omega t minus phi 0 to t 1 by t 1 by t. So, because this integration is 0, because this integration is 0, it is 0 plus j 0. So, you equate the real part it is 0, you equate the imaginary part, it is also 0, and even if you take it as n times, this is also going to be equal to 0. This I am now leaving it to you to complete. So, this is also going to be equal to 0. So, coming back to this instantaneous power, it is Vrms Irms cos of phi minus cos of 2 omega t minus phi. This is a pulsating power, this instantaneous power is a pulsating power at double frequency at 2 omega value with an average of Vrms Irms cos of phi. This one cycle average power is also just indicated by capital P, which is Vrms Irms cos phi. Its unit is watts, is called the average power. So, this is the only power that really you are on an average. The rest, see the pulsating power, because it is becoming positive and negative, this particular component, because it is becoming positive and negative, what it basically means is the power comes from source to the sink, again the same pulsating component goes back from the sink to the source, again comes back from source to the sink, and this happens at a double the frequency. So, this game is played twice fully in one cycle and with no zero average. So, really this does not do any work for us. In fact, however, because the current flows and there will be some resistance in the wire, it will cause loss. So, this pulsating component is not a very good component. Also, suppose you had a single phase AC generator and it is running at constant speed, let us say omega, and this power is pulsating, then what it means? It means torque is pulsating. If you had torque as constant, then the speed will be pulsating and it will cause unnecessarily extra wear and tear in your device. So, we are not very happy about this pulsating part of the single phase supply, and this actually is the motivation for the 3-phase power supply that I am going to discuss. One motivation I have already talked with you earlier about the one motivation was that I can use the geometry of my supply in a much better way. The other motivation is that I will show that I can get rid of this pulsating component by going towards a balanced 3-phase supply. But before I go there, now if I look at this in a phasor diagram perspective, this is my V phasor, this is my I phasor. If this is a phi angle, I have projected this as I cos phi, and therefore, this component I sin phi, the quadrature component from the quadrature component I sin phi, I have not been able to get no effective work. I have not been able to get any effective work done. Why I am not able to get any effective work done? Because this component is actually representative of that double frequency oscillating or pulsating component. So, because of that I am not able to get any work done. So, I define what I have from what I could not get any effective work done as V I sin phi as a reactive power. I define this as reactive power. Its unit cannot be watts, because I am not going to get any work done out of it. So, voltage into current is V into A, and I just use a small r or a capital R to indicate that it is reactive in nature, means it is just happening due to some reactiveness of the system, but does not actually do any work to us. And so, now if I look at V I star, then V I star is going to be V into e to the power I to the power minus j phi star which is V into I to the e to the power j phi, which is Vrms, Irms, Vrms, Irms. So, therefore, Vrms, Irms cos of phi plus j times Vrms, Irms sin of phi, and this is equal to V I star, which is called as an apparent power, a complex power P plus j q, and this P is Vrms, Irms cos of phi, q is this is watts, this is Vrms, Irms sin of phi, volt amperes reactive, and this is also called as the complex power V plus j phi, and the magnitude of this, which is square root of p square plus q square, which is nothing but modulus of V times of I. The modulus of, when I look at the, when I take the modulus of this, I look at the modulus of this, then it is just the modulus of Vrms times Irms volt amperes. This is known as the apparent power. So, I think we will stop here today and continue these concepts in the next class. Thank you.